Hello, good day. Today we are going to discuss about different simulation, quite interesting simulation, and this is going to be dealing with thermo simulations or thermal analysis. So till the previous episode, we had been discussing more about the structural aspects of a product, and we had seen the various types of situations that a structure can be subjected to. We had seen how the structure is going to deform and change shape, okay, based on certain loads, and we have also seen what would happen to such structures when subjected to sudden impact loads or loads depending on certain conditions, say something like earthquake or seismic or wind, etc. We have also gone through certain uh, situations where the system itself uh, takes part in two or three different mm, mechanisms or mechanics. We can say it as mechanics. So, apart from structural, there could be simulation from the fluid dynamic aspects. Apart from the structural dynamic aspect, we also have gone through the fluid dynamic aspects or hydrodynamic aspects. And we have seen certain examples or certain problems based on those kind of simulations. So today we are going to see the thermal simulation by using the finite element method on an automotive projector lamp. So what you see on the screen is an automotive projector lamp. It's a projector lamp. Okay, it can be automotive headlamp or a tail lamp, or it can also be the headlamps of battle tanks. Okay, and it can also be huge projector lamps that is found generally around the buildings or shopping malls and those. So these kind of projector lamps, why we call it as a projector lamp is the intensity of light is projected to 2x or a 3x or a 5x kind of intensity. So which means the light intensity is going to be increased, okay, with the use of certain optical devices, optical reflecting surfaces. Okay, that's what we use generally in any kind of lamps, even torches and all this. We have a reflective surface, and based on the design and the kind of material that is used as the reflective surface, okay, there is going to be the projection. So here we are also bothered about thermal situations. The reason because the light intensity that is going to be projected from the lamp, it is going to be of a certain candescence, okay, and there is going to be a good amount of temperature that is going to be generated out of these systems, and that is the basic reason that we find that these lamps, when designed, they also are designed in such a way that they have thermal fins, and these structures that you see behind the projector lamp. So this is the projector lamp container, and behind the container is the fin, and these fins are provided for reducing the temperature of the system. So there will be air that will be acting as a medium between these gaps, and these air will have a certain factors, convection factors. So when the air gets trapped between these fins, okay, the temperature will be reduced. So the temperature of that particular fin will be removed by the air. Okay, so now this is a process using finite element method, and we are going to study how the thermal simulations are carried on these particular systems. So this is the three-dimensional model of your lamp, the projector lamp, and we have the bulb at the center. Okay, and this is the reflective surface. The surface what you have inside is the reflective surface. Okay, and that has got a certain radius of curvature. So this radius of curvature is suitably designed based on the requirements. Okay, so now behind the lamp there is a system. There are some vertical structures which is being designed, and these are called fins. And these fins are responsible for reducing the temperature of the entire closure. So this is the enclosure, and this enclosure is going to get heated up, and it's made of a certain alloy. And then there is going to be a rise in temperature when the lamp is brightened up. Okay, so now when the lamp is brightened up, there is going to be a certain intensity of light which is going to be thrown out of that. Okay, at the same moment the entire structure is going to get heated up. Now it can go up to a temperature of even 400 degrees or 500 degrees or say 1000 degrees, depending upon the kind of lamp that we are using. Okay, so now very high beams, very extremely high beams. Okay, the bulbs can go up to a temperature, okay, of say thousands of degrees. Okay, so now in order to reduce that particular temperature that comes out of the system, okay, so because there is going to be a huge amount of thermal radiation that is going to be polluting the environment. Now these kind of temperatures can cause infrared pollutions also, thermal pollutions. Okay, so now the objective of this particular project or this particular example is to design a suitable fin, okay, that will be more efficient in reducing the temperature of the system. Okay, so what we have done is we have applied the proper boundary conditions, and we know that we have assumed certain things in mind. The reason because like stresses, like the structural mechanics, the stress values, okay, can have to be analyzed across the thickness. So now this has got a certain thickness, the wall thickness. Okay, so now it's a 3D model, and the 3D model, when we split it into half, okay, so let's say that we are going to see the sectional part of it. Okay, so now this particular thing, when it is cut, okay, so this is how the sectional part is, and it's along the x-axis. I am cutting it. So this will be the thickness, and this thickness, the temperature from the inner zone will reach the outer zone. Okay, so now the temperature has to, the heat has to travel from the inner curvature to the outer curvature. So this is called as the thickness. And now we need to model the system in such a way that because of over stiffness of the elements, okay, we should not be losing the accuracy of the simulation. Okay, so what we are doing is we are going to very carefully mesh this using hexahedron brick elements, and this is again isoparametric in nature, and these hexahedron brick elements are lesser stiffened than the tetrahedrons or any extensions of triangular elements. So here I am using a hybrid element, and these hybrid elements will be comprising, it can have prisms, it can have wedges, it can have hexahedrons. Okay, so all these are going to be contained in the model, I mean the geometry. So this is going to be the meshed model, I mean the 3D model. And now from the 3D model we are going to carefully mesh it with the meshing processes. Okay, now since it's a 3D model, there is a certain process in which you can convert the elements we can split every model. This particular model can be broken into about 10 parts or 15 parts or 20 parts, depending upon the requirements, and individually each parts can be meshed. Now we have different processes like applying it on the surface, okay, and extruding the surface or revolving the surface. So initially the surface elements or the plate elements uh, can be used. The plate elements will be quadrilateral plate elements, and these plate elements can be either extruded or revolved or glided or swept. And there are a lot of processes, the geometrical processes. So similarly, these geometrical processes can be uh, uh, performed, can be used, and these elements, the quad elements, I mean the plate elements, can be extruded into 3D solid models, hexahedrons. Okay, so the similar kind of thing is what we have done here. And after that, what we do is we have to apply the proper boundary conditions. So now, since this is going to be clamped at the bottom, so there will be a constraint mechanism which is going to be subjected. I mean, this particular system is going to be subjected. The area beneath the, yeah, so these are the nuts and bolts, and the area beneath that has a hole here, and that is going to be mounted on a certain structure. So that's the reason we have provided a bolt hole there. Okay, and now this particular projector lamp is going to have a knuckle arrangement, a kind of hinge arrangement on this. Okay, and that can be lifted up, or it can be rotated in that particular region. So now what we do is we are going to find out the stresses, okay, which is formed because of the heat. Okay, and now before that, what we need to do, or what we need to perform, is a thermal simulation. Now the thermodynamics, okay, the thermodynamics is a subject that is going to be dealing with the heat and energy and all this. Okay, so this is well known to us. And now here there are certain parameters or certain inputs that is going to be prominently used. Okay, there are inputs that we use for structural mechanics, structural dynamics, structural simulations. So the main properties are going to be the Young's modulus, the Poisson's ratio, and the density. Okay, so now here there is going to be another parameters that is going to be involved: the coefficient of linear expansion, the heat flux, okay, the convection coefficients. Okay, so these are the parameters that will be used extensively for performing thermal simulations, and the rest of the other things will be the same, like the structural simulation, wherein the static structural simulations, we don't have any time dependent functions, so that will be assumed that everything is happening in a stable environment. Okay, so when we perform a dynamic simulation for a structure, what we do is we are going to change the parameters with respect to the time. So the loading can be varied with respect to time. Okay, it can be a point load, it can be a rolling load, or it can be a shaft load, it can be a wind load, it can be a earthquake load. Okay, any kinds of loads. Okay, when it is varying with respect to your time t, okay, that will be called as a transient simulation. So similarly here, okay, like structural simulation, we can perform a thermodynamic simulation or a thermal simulation, but that will also have two types of simulations. So how in structural we have a static simulation, here we call it as a steady state simulation, and how we have a transient simulation in structural analysis, and that we refer to structural dynamics. Here also we are going to have a transient simulation. So apart from the static, the steady state, there will be a transient heat transfer. And now this transient heat transfer is a situation where we would like to study what will be the change in heat, how the heat is going to be changed from the source to the sink, how it is going to be transferred, and what are the processes through which the heat can be dissipated from the system. Okay, so here similarly we have three different ways of thermal transfer. One is going to be conduction, the second one is going to be convection, and the third one is going to be radiation. And now this being a steady state heat transfer, okay, everything is in an assumption that there will be conduction happening and there will be a convection also. The conduction, we can say that the projector lamp is mounted onto a knuckle system, a mount, okay, and this mount and the lamp is getting connected with a bolt and a nut. Okay, so here there can be a conduction transfer between the two bodies. Okay, so now the convection is assumed that air is going to be the medium which is going to be covering this particular projector lamp. Assuming that this particular lamp is going to be working in a an environment where air is dominant, and then that air has got a certain ambient temperature, okay, and there is a certain flow for that air, and there is a wind, and okay, based on that particular wind, the air is flowing on some, at some particular velocity. Okay, so these are all the assumptions what we make. Okay, so now since this being a steady state heat transfer, okay, that is the reason we make these assumptions. Now actually, when we get into the complex analysis or simulation of this particular lamp, what we do is we better perform on computational fluid dynamics, and we define the heat sources, and we also define how the air, what is the medium, and what is the temperature of the ambient temperature, and what is going to be the temperature of the system, and based on that, performing a computational fluid dynamics, okay, we will be able to see the airflow. And now in computational fluid dynamics, we will be also able to find out the trajectories, the air trajectories between the structure and how it is transferring or removing heat from the structure. Whereas here we won't be able to visualize the air trajectories. Instead, we'll be able to see the conduction part, because of the air. Okay, because the air is acting as a film and it is sticking onto the every metal surface of the lamp. Okay, there is a convection parameter allotted to the structure. Based on that convection parameter, the system will be able to have an intelligence and assume that there is air. Air is the medium, and air is at this particular temperature. And when the convection medium is air, what will be the change in temperature? Okay, so Q is equal to M into C into delta T. We know that quantity of heat will be depending upon the mass, the specific heat, and the change in temperature. Delta T is nothing but the T2 minus T1, or the sink temperature minus the source temperature. Okay, so now based on that, we are going to perform a simulation, and we are giving the inputs. Okay, so now what will be the kind of inputs? The boundary conditions. We have a boundary condition, and we define that the system is going to be constrained, and how it is going to be constrained, that you will be able to see it here. Okay, so now we are assuming that this is mounted, the projector lamp is mounted onto a knuckle system. Okay, and this mount, okay, we are going to constrain it. Okay, so the assumption is the projector lamp is going to be constrained at the bottom. Okay, and now there is a bulb inside, and we have the fins designed outside. So now let's see the thermal loadings. So now in the thermal loading, we are going to define what is going to be the temperature. So the temperature we are giving it as 89 degrees Celsius. So let us assume that the temperature of the source, the bulb, is going to be about 89 degrees, and that 89 degree is going to be, applied as the heat source, and based on that we are going to find out what are the temperatures of the surrounding systems. Okay, and now apart from the temperature of the heat source, I mean the bulb, we are giving the convection factor, the convection coefficient of air. So here we are giving it as 2.5 e raised to minus 5 watts per millimeter square. So that will be the convection factor, and we are giving the convection factor to the surrounding mediums. Okay, and then we are also giving a heat flux. Now the heat flux value is 0.000425 watts per millimeter square. Okay, and then we are applying it to the internal surface. That's the heat flux of the material. As I told you, there is going to be a reflective surface, and that reflective surface is going to be inside, that is going to be coated, and that reflective surface is the reason for that beam, the intensity of the light intensity, to be magnified to say 2 folds or 3 folds or 5 folds, okay, depending upon the light. If the light is capable of generating say X units of heat, or light, now with that particular reflective surfaces painted, that can become 6x or 10x. Okay, so now that capability comes from the reflective surface. So for that we are applying a heat flux. So the main parameters, apart from your density, Poisson's ratio, and Young's modulus, for a thermal simulation to be, the basic thermal simulations of dynamics to be performed, are the temperature of the system, the temperature, the convection factors. So what is going to be the convection? Whether it is going to be air, whether it is going to be nitrogen, whether it is going to be water, or whether it is going to be any other gases. Okay, so now each gas has got its own convection coefficient. Okay, so similarly we are also identifying the reflective capacity, the reflective surfaces. So each reflective surfaces has got this much incandescent of candela of light. Okay, candela is the unit of light. Okay, and this much candela of light can be reflected. Okay, so now based on that, every reflective surface, okay, the material parameters, the properties, there will be a heat flux also. So we are also defining what is the heat flux of the system. If it is air, the air has got a certain heat flux. Okay. So based on this, we are going to run the simulation. Okay, and once we run the simulation, we will be able to identify like what are the temperatures around, across that thickness part. Okay, so now once we perform the simulation, okay, I have already run the simulation, and then this is going to be my simulation results. Okay, so now I have a temperature. Okay, so now the temperature plot is this. So here you will be able to see the contours. Okay, so this is going to be the temperature contour. So you will find, the entire projector lamp is broken, or it's meshed using hexahedral brick elements. Okay, and now these hexahedral brick elements are going to yield me the best results, and that is the main reason for me to use these kind of isoparametric elements. Okay, so now after performing the simulation, I have got my results, and now let's see the contours, the temperature contours, how it is going to be. Yes. So here the maximum temperature is in the back portion, which is about 89 degrees, and the rest of the other temperatures are going to be lesser than that. So you will find it will vary the stand, the mount is blue in color. The mount region has got a temperature of say 42 degrees. Okay, and the region that is going to contain the lamp. So the interior portion, you will find there is a lamp here, and this lamp is going to be of 89 degree. That's the assumption. Okay, so now 89 is a value that I have given, just like that. It need not be 89. It can be about 890. So now if I give the temperature as 890, then that will sound more realistic actually. Okay, so when the temperature of that particular bulb is about 89, we are getting the temperature, and we can also find how that is getting distributed, how the temperature, across the section is getting distributed. Okay, so here we are able to find out how uh, okay, so yeah, so here we'll be able to find out how the temperature variation is going to occur. Yeah, this is the section, and across the section we are able to find out the temperature. Yeah, so the bulb temperature and across the thickness how that variation is taking place. Okay, so let's see what is going to be the thermal gradient. Yeah, this is going to be the thermal gradient. So the thermal gradient looks like this. Okay, so the interior region, okay, the region that is blanketing or covering that particular bulb, you will find the gradient results. I know the maximum is 1.32 and the minimum is say of course 0, but still let's say it is about 0.1, 0.2. So the thermal gradient is nothing but it is like the deflections or the displacements what we see. Okay, so in the uh, structural simulation when we perform, there is going to be a stress value, and then you get a deformation value as a result. So similarly here, temperature is going to be a factor. Okay, and the thermal gradient is going to be a factor. So this gradient we generally assume it as uh, the deformation part, whatever we say in the structural simulation. Okay, now what we can do is we can try to identify like how it is getting dissipated, how the heat is getting dissipated. Okay, so now you will find that the temperature of that particular region, the central region, the bulb region, let us say the temperature. So from the bulb region, we will see the red contours getting converted. Okay, so by the time it comes to the outer surface, the projector outer surface, the temperatures are going to be in the range of say 65, 70, etc. So now the biggest problem here in this simulation is here we'll be able to just find out like we'll be able to get an idea about what is going to be the temperature, what is going to be the gradient, etc. Now it's very difficult for an engineer to visualize At time t is equal to 10 seconds, what is going to be the temperature? Or time t is equal to 3 seconds, what is going to be the temperature? Now, each moment, how the structure, the temperature of that particular system is going to increase and how it is going to decrease. In order to visualize those kind of systems, we need to get into an advanced modeling system. Either we go to the transient simulation or we get into the fluid dynamic simulation, CFD simulation. Okay, so with this, let's close this particular simulation, and we will try to discuss like what are the objectives, okay, and what exactly is the reason that we perform a thermal simulation, why we perform a thermal simulation. So now, depending upon the system, depending upon the kind of industry vertical, the temperature, I mean, the things can change. The product, the objective of the product can change. Now, let us say a coffee supplier, like Coffee Bean or Barista. Okay, so they want to please their customer, and they want to ensure that the customer has got 100% satisfaction. The customer, sits there in their coffee shop, okay, and they would try to enjoy the coffee, and in between that there is absolutely no issues or problems or you know worries that comes into the customer's mind. Okay, so now they try to make certain things very sleeky. They try to design. I mean, they try to make their system itself to please the customer. Now, one such process is by creating an environment, an ambient environment in that particular coffee shop. Okay, and apart from that good ambience, the utensils that they use should also be more interesting. Okay, so it should be very ergonomic. The customer should be able to easily hold the cup, the coffee cup, and even if the coffee cup is held by the customer should not be able to feel the heat of the coffee inside. Okay. Now for that, the particular coffee cup is made, designed in such a way that the very hot, very high temperature coffee which is inside the cup, okay, has to be handled by the customer, and the customer shouldn't feel the heat while gripping onto the mug, the coffee mug or the tea mug. Okay, so the coffee shop or the coffee company is placing an order, okay, from to the manufacturer of the cups. Okay, they say like we need the customer to be there in the coffee shop for a while. The customer should be very pleased, and the customer should also, customer should be ergonomically happy, or like there should not be any issue or in holding the mug for a long time, and it should be very simple, and the heat should not be easily, he should not feel that particular heat, he or she should not feel that heat from the mug. And at the same time, the mug should be in such a way that it should be similar to a flask where the heat, the temperature of the coffee, okay, remains in the mug for a certain period of time. Okay, so this is the specification given by the coffee shop owner to the manufacturer. So the manufacturer, when designing the coffee cup, he designs it from every possible way. The handle, okay, the brim of the cup, okay, and what would be the angle of the cup, the slant angle, what would be the radius of curvature of the cup, okay, and now at some angle when the customer is going to tilt his hand, okay, so the coffee should not spill all of a sudden, so that the cup should have a proper radius of curvature, so that even when he is trying to sip it by bending or holding, by bending his arm, okay, the coffee should not spill out, Okay, and at the same time, the coffee contained in the cup should also have the temperature. The temperature should be, reducing from the coffee cup in a specific time. Say the first 5 minutes this much temperature, and then the next 5 minutes the temperature is going to decrease by this much percentage. The third 5-10 minutes the temperature will drop by this percentage. So even at the end of 15 minutes or 20 minutes, there should be a that particular temperature of the tea or the coffee should be optimal. Okay, because some customers they don't like cold coffee. Some people they would like their coffee to be always warm. Okay, some people they finish it off very fast, very rapidly. Okay, so now the temperature of the coffee, let us say it is about 99.99 degrees Celsius. Okay, that is impossible for somebody to gulp it out. Okay, so they will wait for the temperature to reduce. Okay, the time taken for the temperature to reduce from 99.99 degrees to about 60 degrees, or say about 50 degrees, it will be about 15 minutes or 20 minutes, or probably 25 minutes. Okay, so now if the container or if that particular mug or the coffee cup is going to be made with a very weak material, very poor material in conduction, very poor material in what do you call coefficient of linear expansion and all those. Okay, so what happens is the temperature can reduce faster. So maybe in 5 minutes, okay, probably 5-10 minutes, the complete temperature can come down, and the customer will get irritated. Okay, because the customer would have probably come there with a different person and is discussing some business, and that particular conversation might take about half an hour. Okay, and it should be ensured that the temperature of the coffee should at least be almost closer to some 60 degrees. Okay, even at the end of 20-25 minutes. Okay, so now such coffee cups or mugs can be designed through thermal simulation, steady state heat or transient thermal simulations, where it is going to be time dependent and the functions are going to be given. The first 5 minutes the temperature is going to be this, reduced to be this much. The change in temperature delta T is going to be this much. The next 10 or 5 to 10 minutes it is going to be again the change in temperature delta T1 is going to become delta T2. So like that for the entire half an hour, say about 30 minutes, we are going to define a curve, a function, and that particular function will be mapped with respect to the temperature versus time function. And now once this function is given, okay, as an input to the problem, okay, the system is going to solve it. The system is going to have in the mind that the temperature is going to vary from this temperature to say 99.9 degrees Celsius to about 60 degrees, and the time taken for that is about 30 minutes. And in this 30 minutes, the first 10 minutes it should be like this, the second 10 minutes it should be like that. So once that particular function is applied, we'll be able to identify all these parameters. We can find out what will be the heat flux, we can find out what will be the convection factors. Whatever we have done here, the reverse of it can also be determined, and we'll be able to find out the coefficient of linear expansion alpha also. And once we get the coefficient of linear expansion alpha, from that alpha we will be able to find out what would be the most prominent or suitable material that will be able to that can be used for making this particular coffee cup. Okay, so today let's wind up with this particular simulation here. Okay, and well, the next episode I'll be coming with the same projector lamp, but then with a transient simulation. Okay, and we'll try to find out how the temperature is going to be dissipated over a period of time. Okay, and then the next two transient simulation will be trying to make use of computational fluid dynamics, and we'll try to find out how the temperature is going to vary with respect to time, and how the the fluid, the convecting fluid, how it is going to carry the temperature from one point to the other point. So those velocity, I mean the temperature vectors, the heat gradient vectors will be able to find out. Okay, so let me before concluding, let me just tell you once again, please subscribe this channel. You'll be able to find many interesting videos like this. You can communicate, you can talk to your friends, you can discuss it with your friends, we can form definitely some forums or groups, and then we can definitely have a very interactive session, and very complex simulations can also be performed, and each one can share your ideas, each one can share your kind of views about the simulations, and you can also share your problems, any new problems that you have which you feel needs to be solved, okay, and which you feel is a bit tricky and which needs to be solved in a proper way. Okay, everything can be done. Okay, and let me, before concluding, let me once again remind you that please go through the videos, the past videos, whatever we have done. Okay, this is to those who are regularly watching this channel. Okay, so kindly go through all the videos, because each video is going to be dependent on one another. Okay, so the concepts or the domain, the technical part or the domain part, okay, the actual science part of it, you will be able to understand from the other previous videos what we have made. Okay, and you can correlate it. Okay, so I believe this is going to be the first temperature based simulation. Okay, and let's try to make it more interesting in the coming episodes. So kindly subscribe and share with your people. Okay, thank you very much.